hear from Professor Frank Iardino.
Right, thank you. All right, so tonight's talk that I want to try and cover in about 40 minutes is on transplant immunology and transplantation, mainly focused on renal transplantation, but it's really talking about the drugs themselves. And I want to try and cover a few areas. I'd like to cover, firstly, really try and understand the allograft response. And there's two things we need to consider when we're thinking about that and immunosuppression and the allograft, the host response to the allograft is, firstly, that there's donor and donor retrieval factors and ischemia reperfusion. And then there's the classical adaptive immunity. I want to cover the immunosuppressive drugs that we use and you really cover the site of action, remembering that, in terms of action and site of action, whatever we discuss tonight applies to the drugs generally, whether you use them for autoimmune disease or other organs. How we detect the anti-HLA antibodies in terms of the allograft response, that's probably changed over the last 5 or 10 years. And look at the immunopathology of rejection. That's at the moment, our clinical gold standard for diagnosing rejection and how that defines treatment, and then some clinical outcomes from all that. So hopefully by the end of it, you'll be able to sort of understand how alloactivation and immunopathology and the pharmacology allows us to understand immunosuppression, predict immunological and clinical outcome of transplants, how to personalise our therapies, which is really where really medicine is moving towards, personalised therapy, and how we can look at preventative care in some of these patients and look at their outcomes and how we might prevent the adverse outcomes. So we'll start by going through the allograft response, and I think the first thing, as I mentioned, ischemia reperfusion is quite important, and that is the donor retrieval of the organ itself and the storage of the organ leads to cold ischemia time and warm ischemia time. I'm not going to go into how those each contribute, but that certainly leads to ischemic injury of the organ. And then when you reperfuse the organ, that certainly the ischemia sets up and primes the organ, causes the injury. The reperfusion then causes the inflammation, the so-called ischemia reperfusion injury. That then activates the innate immune system and triggers off inflammation, which involves macrophages, neutrophils, and NK cells, and also leads to dendritic cell, presenting cell maturation. I'll show you how that happens. And that then leads to the dendritic cell maturation is the key part of the classical allograft response, which is the adaptive immunity, which is the presenting cell T cells and B cells, and that's what we generally talk about, but in fact, really it gets triggered off and sets in place and amplified by the ischemia reperfusion injury. What's important in ischemia reperfusion are the toll-like receptors, and particularly 2 and 4. And these toll-like receptors, as we probably heard in other lectures, are recognition receptors of pathogen-associated molecular patterns, or PAMPs, which lead to protective immune responses to infective organisms, but also through injury and release of endogenous factors, so-called DAMPs, leads to the release of things like HMGB1, which then mediates inflammation and that ischemia reperfusion and that so-called sterile inflammation. And that's quite an important response, which has really been understood in the last, in the last little while. Now, the innate immune system and ischemia reperfusion leads to upregulation of these toll-like receptors, the HMGB1. There are a whole lot of other things that get released, heat shock protein and others. These important molecules then mediate inflammation through things like NF-kappa B by binding to the toll-like receptors and other receptors such as the RAGE or the advanced glycosylation end product receptor, also called RAGE. That then sets in place activation of macrophages, neutrophil, dendritic cell activation and maturation, leading to alloactivation and the adaptive immune response. What's important here is that the toll-like receptors act through pathways. The so-called MYD88 is the signalling molecule for these receptors and other receptors, and these trigger off inflammation. There are agents now being developed that target those pathways, and so you will see over time therapies targeted at the donor and the donor organ ischemia reperfusion injury as time goes on. And these have been conclusively shown to be involved through various laboratory experiments where they've actually knocked these receptors and pathways out. Also to say that that the release of ATP, which is in fact through necrotic cells and so forth, is pro-inflammatory, and so other pathways through these P2 receptors. And there are protective pathways through CD39 and 73 which convert ATP to adenosine, and adenosine being act on adenosine receptors which down-regulate inflammation. So these are protective and these are pro-inflammatory. And they act through macrophages, lymphocytes, and even possibly regulatory cells, neutrophils and NK cells. So these are the pathways that are important in ischemia reperfusion injury. Now, once the organs then is in the host, then you get the classical adaptive immune response where you get a presenting cell with a host T cell, which then gets activated through recognition of either a self-APC with donor peptide or with a donor APC that stimulates a host T cell. And that, as we know, involves three signals. Signal 1 through the T cell receptor, signal 2, which is co-stimulation, and that's important. These are all therapies, these are all pathways where therapies are actually targeted, and I'll show you where our immunosuppressive drugs work. And then there's signal 3, which then 1 and 2 leads to activation, transcription of cytokines, and then signal 3 through the cytokine receptors leading to T cell proliferation. These are the intracellular pathways involved, calcineurin being one of the key factors. These pathways are all pathways where therapy is being targeted towards, as is the co-stimulation pathway. The best known one is belatacept, which is the CTLA-4 co-stimulatory pathway being targeted, and then the cell cycle replication, and there are, we know, drugs targeted at that, such as mycophenolate and others. And that leads to T-cell activation and cellular activation, and then these migrate into the organ causing cell-mediated rejection, which we will diagnose through our pathological or immunopathology and our pathology when we do the biopsies. This is just looking at that pathway in a bit more detail, just to say that the signal 1 and 2, these cytokines that are released, it's not only IL-2, there are others like IL-15. They act on the receptors, and they then target through kinases and other signaling molecules like mTOR and these JAK kinases, remembering, and I'll show you where these are actually targets of our therapy to indicate where these this pathway being a key pathway to then lead to DNA replication and T-cell proliferation and amplification of the T cell response. And these are all pathways that are targeted by our therapies. It's also important to know that T cells and B cells talk to each other, and that B cells then get activated to produce antibodies. Again, very similar. B cells are presenting cells through the class 2 on B cells, talk to T cells. They activate and talk to each other. T cell help causing B cells to maturate, predominantly through CD40 and maturation of the B cell to produce anti-HLA antibodies, remembering that the target of the rejection response is donor HLA. And that B cells also lead to, as presenting cells, continually activating T cells. So this is a two-way interaction leading to predominantly the production of these antibodies, which are targeted to donor MHC, which then migrate into the organ, leading to antibody-mediated rejection. So rejection being a cell-mediated response and cell-mediated rejection, and an antibody-mediated response, antibody-mediated rejection, the target always being predominantly donor MHC and their donor target cells. And where do our therapies work? Well, if we look at this simplified diagram, we see that calcineurin inhibitors, cyclosporin and tacrolimus, act as signal 1, calcineurin being an important phosphatase that is important in this signal 1. CTLA-4 belatacept acts through co-stimulation, and I'll show you how that's used clinically. The signal 3, anti-CD25, our anti-CD25 antibody that we use clinically, again acts at the IL-2 receptor site. mTOR inhibitors such as sirolimus, everolimus acts through blocking the mTOR signaling from the receptor down to the DNA level. Mycophenolate azathioprine acts at the level of the DNA and DNA replication. And we've got anti-T cell therapy or depletion antibodies that basically just deplete that T cell. That's where they work. So that's if you're targeting, cell-mediated rejection. If you're targeting antibody-mediated rejection, then what we do is try to remove these antibodies through plasma exchange, modulate through IVIG, and other therapies which have not been proven but have snuck into the transplant literature, anti-CD20 and the proteasome inhibitors. But these are obviously not used routinely and still to be proven as effective as targeting antibody-mediated rejection. But certainly plasma exchange, IVIG is certainly used, and there are some units that are using anti-CD20. Now, the other thing is that I wanted to point out is how we detect these anti-HLA antibodies, and that has changed quite a bit. There are three ways. The oldest way is through cytotoxicity, and we still use that clinically, by the way, when we do a cross-match on the evening when a donor organ comes up. The cross-match needs to be, the T-cell cross-match needs to be negative for that organ to be offered, where it detects anti-HLA antibodies. More sensitive methods are through flow cytometry, and in the last 5 or maybe more, 10 years, these solid phase assays, which are beads coated with HLA that pick up anti-HLA antibodies in our donor, and the readout is the so-called mean fluorescence intensity or channel shift in our assays. And the sensitivity is Luminex, certainly more than flow, certainly more than cytotoxicity, and there are these Luminex detected antibodies through MFI is being used clinically and is being used to determine whether we allocate and how we allocate organs to our renal transplant recipients. And there is a cutoff above which we say no, that organ to that individual. if the patient's got anti-HLA antibodies detected by Luminex above a certain threshold. And so it is something that is used clinically. Just to say that there still is a lot to be learned about these antibodies, and we know using these assays like Luminex, and what do I mean by that? There's a lot to be learnt. We do use them because we know above a certain threshold, for example an MFI of 4,000, which is where we use our cutoff, that the outcome is not good. But below 4,000, we know that we have got these patients that, and there's through retrospective studies showing in the presence of donor-specific antibodies detected by Luminex, which is the most sensitive, about 40% will end up with acute antibody-mediated rejection. About a third end up with subclinical rejection. But there are a number of patients with these very low-level antibodies for which there is no antibody-mediated rejection. And so we are learning to use this assay and what these low-level antibodies mean and how we can more clearly define which are the ones that are going to go on to a worse outcome and which ones may not go on to a worse outcome, and what do these mean. And the reasons for that, why do we see these patients with low-level antibodies with no evidence? And, because these are fairly sensitive assays, as I said, assays with MFIs under 4,000. Why do we see them? Well, there are probably a number of reasons. People have looked at the isotypes, and we know that there are complement-fixing antibodies, anti-HLA antibodies, and which are the IgG 1 and 3, and then 2 and 4, there's sort of non-complement or poorly complement-fixing antibodies. And people have shown that, that these subclasses and whether they fix complement or not may relate to why some are pathogenic and some are not. It's not as clean as what I'm trying to make out at the moment, just to give you an idea that we are trying to learn how to use these antibodies at a very low level. And for example, the IgG3, which is the complement-fixing antibody, we do see that there is a tendency, if you get induced antibodies, early rejection, microcirculatory injury, as opposed to IgG4, which is a non-complement-fixing antibody or poorly complement-fixing, which tends to cause late rejection and associated with other more sort of subacute causes. So just to mention that, that there is all this still that's going through the literature at the moment, and there's still a bit to be learned. But we do use them clinically, as I said, above and below these absolute thresholds determined by MFI, and it is used in terms of how we allocate organs. The next thing I'd like to move on to in terms of defining a rejection is to give you an idea of our current gold standard, which is histologies. So the Banff classification is an international standard classification of renal transplant pathology, which defines rejection. It is used in other organs. I'll only talk about the renal organs at this, the renal transplants at this stage, and to say that this does define pathology, and it does define it in terms of cell-mediated rejection, as I mentioned before, and what therapy we use for that. And it also defines antibody-mediated rejection, and as I showed you, our therapies that are targeted towards that. So I'm trying to give you the idea that pathology, immunopathology, mechanisms, understanding that, and with our gold standard Banff classification, it does direct our therapy of rejection and what immunosuppressive drugs we use under what circumstances. To say that the Banff classification has undergone a number of changes over the years and has been modified. The only point about it, this is the current Banff classification, to show you that it defines a number of different categories, sort of 1 to 5 or 1 to 6, normal looking tissue, antibody mediated rejection, and how that's defined. Not that you